Okay, so question 1 of this set of past paper questions on magnetism and electromagnetism. It asks, a magnet produces a magnetic field. What does the magnetic field pattern look like around the magnet? Well, it can't be either of these two, because here the magnetic field is not shown as going from one side of the magnet to the other, because actually it goes in a loop from one pole to the other and through the magnet to form the loop that way. This is the magnetic field pattern we would see around a current carrying wire, so it's definitely not either of these two. Picking between these two, we need to look at the direction of the lines. The lines should be going from north to south, so it is this one. Question 2, it says one block is a permanent magnet, one is iron and one is aluminium. This is iron is a magnetic material and aluminium is non-magnetic. Okay, so one of these will find that and one is a permanent magnet. Now it describes how another permanent magnet can be used to identify the block. So we can say that point number 1, the permanent magnet has no effect on the aluminium. So if we bring our permanent magnet to one of these blocks and it has no effect, then that's going to be the aluminium. The second thing we can say is that the permanent magnet in any orientation, so whichever way around we put the poles, always attracts the iron block. So the iron block is a magnetic material that it becomes an induced magnet when it's close to a permanent magnet, and the force between them is always attractive. So and then finally we can say the permanent magnet can, forgot the word magnet, the permanent magnet can attract or repel the other permanent magnet. So when we are thinking about one of these blocks, it's a permanent magnet. If we bring the other permanent magnet up towards it, it can either attract in one direction, and if we flip the magnet around, then they will repel. So this question asks about, shows us an example of a toy crane that's using an electromagnet. So it uses the electromagnet to pick up and move the blocks, and we have to be able to explain how the electromagnet is able to pick up and move the blocks. Okay. So to get full marks, the 6 marks, it's more than just giving 6 points. We need to form a logical argument to answer the question. Okay, we need to form a logical argument. So let's think about this in stages. Okay, so to pick up the blocks, and remember these are made from magnetic materials, so they're always going to be attractive. The electromagnet needs to attract the blocks. Okay, to be able to pick them up, it needs to be able to attract the blocks. This is done by closing the switch. Alternatively, you could have said, as it said in the mark scheme, completing the circuit. So closing the switch, completes the circuit. So that current flows in the coil of the electromagnet to produce a magnetic field. When the electromagnet is moved close to the block, it will attract the block. Okay. All right, so we generate the magnetic field by closing the switch, so there's current in the coil that generates a magnetic field in the electromagnet to attract the block. Okay, we can then move the electromagnet and block together, so they stay together because they're attracted together, to the new position. Okay, and then open the switch, to stop the current flowing in the electromagnet. As there is no magnetic field, the block is released, it's no longer attracted. Okay, so question 2, we're shown a bar magnet, and here we have to draw the magnetic field around the bar magnet. So the first thing is that the magnetic field is always drawn with these oval shaped loops between the poles like this, and then you would show lines coming out, heading off like this. We can have one in the center that will head off towards infinity. Okay, and we need to add the arrows to show the direction. So the arrows are always out of the North Pole and into the South Pole. So the direction is always from north to south. Next, we have to describe a method to show to be able to plot the magnetic field lines around the bar magnet. Okay. So what we need to do is, number 1, place the magnet on plain paper and draw around it, marking the poles. Okay, that's so that when we remove the magnet, we're able to put it back in the same position. So then we do. Now, you now need to place the compass. You can place the compass anywhere around close to the magnet. They say in the mark scheme, and it's probably a good approach, is to start by placing the compass close to a pole. Okay, so you can start by placing the compass close to a pole. So then we move the compass to line up the tail of the compass needle with the dot that we've already put down, and we mark the position, the new position of the tip of the needle with a second dot. And then we continue doing that until the compass reaches the second pole. And we draw a line through these dots with an arrow and add an arrow from north to south. And we repeat that for different starting positions. So, just so that it's clear what those words are saying, let's imagine we've got our magnet is like this. So we start by putting our compass down like this. The needle is pointing this way, and we put in a dot. So we then repeat that process several times until we end up at the other pole. And we then draw a line through all of these dots. So we're doing dot to dot in this case. And we have an arrow going from north to south. And then we start the compass somewhere else, for example here. And again, we put in a dot. And we repeat the process again. Okay, part C. Explain why the compass needle moves when it's placed near a bar magnet. And we have to say two things here. So they give a set of words in the mark scheme that you can use as well. But essentially the thing to realize is the compass needle is a small bar magnet that can rotate. So it's like this pencil, that would be the North Pole, that's the South Pole. And the compass needle can rotate around its centre. And the North Pole of that compass needle is then going to be attracted to the South Pole of the bar magnet. And likewise, the South Pole of the compass needle is attracted to the North Pole of the bar magnet. So what we have is in the compass, we have, so if here I've got my bar magnet, okay, and my compass is like this. It's actually a little bar magnet as well. So as I bring this compass in close, what happens is the South Pole is going to be attracted towards this North Pole. The North Pole is repelled. So we end up with, it would look something like this. And then we would have our dot because the arrow on the needle would look like this. And as we come round to here, so in this case, if I was to put the compass in here, the North Pole is being attracted to the South Pole of the bar magnet. Okay, next question says, iron is magnetic material, and we just simply have to identify another magnetic material, that is cobalt. The other one we need to know is nickel. Give two pieces of evidence that show the magnetic field of the Earth is changing, right? So there are two things about the magnetic field. We've got its strength and its direction. So we need to see which of these could be changing. Well, we can say that the poles are changing position. This is true that over time the poles don't stay in the same place, they move. And the second thing is that in the past the direction of the magnetic field has reversed. But it's unlikely you're going to be asked, I would say, this question in your exam. What causes the Earth's magnetic field? This is caused by the core of the magnetic field. So this is caused by changes in the Earth's core, and it is due to movements of, for it to be magnetic, it needs a magnetic material, and the magnetic material is iron in the Earth's core. Okay, these two questions, less important, or less likely to appear in exam, I would suggest. Okay, question 3. So we've got a conductor carrying an electric current. It's placed in the magnetic field so a force can act upon it. And we need to know 2 ways in which the force can be increased. So let's remember, force on a current carrying wire is given by this equation, where this is the magnetic field strength, magnetic flux density, this is the current, and this is the length of the wire. We're not going to change the length of the wire because we're dealing with this situation. We just want to increase the force on the wire. So that leaves us with, how can it be increased? We can increase the strength of the magnetic field. That is, increase the value for B. Or we can increase the current, the value for I. State 2 ways in which this force can be made to act in the opposite direction. So remember, this is given by Flemings' left-hand rule. The magnetic field is from north to south. The current is in this direction, which means the force is upwards, as shown in the diagram. I want the force to be downwards. I could do that just by turning my hand around. And what I've done there is the field is still in the same direction, but now the current is in the opposite direction. So I could do reverse the direction of the current. I would, by doing that, by connecting the battery the other way around, or flipping the battery. And the second way I can do it is reverse the direction of the magnetic field. So to put the magnet the other way around. So again, Fleming's left hand rule. What I could do is turn my hand this way, so the current is staying in the same direction, but I'm reversing the direction of the magnetic field. In what circumstance will no force act on a conductor carrying an electric current and in a magnetic field? There is no force if the conductor is parallel. So the key word here is parallel to the magnetic field. So what I'm saying there is, if I have a magnet like this, that's north and south, so the magnetic field is from north to south. If my wire is like this, the current is like that. Here the force is equal to B-I-L. Okay, so the strength of the magnetic field is B, current is I, L is the length. However, if I had my magnetic field is like this and my wire is in this direction, so for example it's a sort of a loop of wire, and I've put it in like this and the current is in this direction, here the conductor is parallel to the magnetic field line, so the force is 0. Okay, and question 4. The diagram shows an apparatus to demonstrate the motor force. Remember, the motor effect, I beg your pardon. Remember, the motor effect is a force on a current carrying wire in a magnetic field. Okay, so that's what we're trying to demonstrate, this force acting on a wire in a magnetic field. And we've got this small piece of copper, and it's just sitting on top of the other wire. So this is making a complete circuit, but this can still move. It can slide along on top of the wires, and it's placed inside a magnetic field. Now, it asks what's going to happen to the wire X. So first thing it's going to say is it will move, you could say, or you could say it will experience a force. That's also acceptable, but that's not going to be enough to get the mark here. You need to add some further information. So what direction will that be? So if I put the magnetic field lines are down like this from north to south, so magnetic field lines are downwards. The current going from plus to minus, so the current comes down this wire, down through here and back through here. So the current is in this direction, which means that the direction that it will move, or the direction of the force, is this way to the right. So you need to say it will move or experience a force to the right. And I believe in the mark scheme they added horizontally. But you need to say to the right because it is Fleming's left-hand rule that we're using here. So it's horizontally to the right. It won't be going up or down, just sliding. What difference do you notice if the following changes are made? If the magnetic field is reversed, well, if the magnetic field is reversed, the force is in the opposite direction. So if we reverse the magnetic fields, we're going to have the forces in the opposite direction. If we increase the current, the force is increased. Now, they said in the mark scheme, if you look at the mark scheme for this question, they said faster movement but not move further. Now, the reason why they said not move further is because this will only experience the force and hence move inside this magnetic field. As soon as it comes out of the magnetic field, there's no magnetic force, and it will come to a stop due to frictional forces as it slides along the wire. So you need to say there, it's easiest to say the force is increased. You can say that the movement is faster or it accelerates more, to be strictly speaking correct. But you must not say it moves further. Okay, and now part B of question 4. So here it shows us an electric motor. So this is a coil that's been placed inside a magnetic field. And it's shown arrows to show the direction of the current. And the arrows labelled F, so the direction of forces acting on the coil. Okay, and it asks us, describe the motion of the coil until it comes to a rest. Now, this is a particularly difficult question because it looks like the electric motor as it's described in the revision guide, but the thing to notice here is there are no slip rings and there's no split ring commutator. So there's no split ring commutator, which is what allows us to have the coil turning constantly in one direction. So what's happening here is when the coil is in this direction, so the current is coming this way through the coil, so the current is in that direction, the magnetic field is from left to right, that means the force is upwards, which is what they show in the picture. The force on the other side is downwards because the current's in the opposite direction, and that will cause the coil to turn. When it makes one full half turn, the current here is now outwards from the magnet. So that means that the force on this side will then be upwards and the force on this side downwards. So let me just sketch that. So we have this initial situation where we have the coil. the current is out this side and in this side, so the force is up there and down there. Okay, so that's situation 1. This will cause the coil to return, and I'm just going to actually, let me show this half of the coil in red so we can follow what's happening. When that makes one full half turn, then now the part of the coil that was on this side is now on this side, and the other half, it's now on this side, so it's turned. Okay, but this side is where the current's coming out, and the red side is where the current's going in. So if I now use Fleming's left-hand rule, magnetic field like that, the current's going in, which means the force is now downwards on this side and upwards on this side. So it started off up on the left, down on the right, causing it to rotate clockwise. Now it's up on the right and down on the left, causing it to rotate anti-clockwise. Okay, so what is the motion of the coil? So initially the coil rotates clockwise. Okay. It then reverses direction and rotates anti-clockwise. Okay, so it's going to be going like this. Now that's the first 2 marks. The last mark is very tricky to get. What you have to realize is that when the coil is in between, so when the coil is in between like this, and I'm trying to draw this as best I can, showing it like this. Now we have the conductors are no longer at perpendicular to the magnetic field lines, so there's going to be no force acting on the coil when it's in this position. So in this position there's a force acting causing it to turn. It will just start to turn, and then the momentum will take it round till it reaches here. That will be pushed this way and then pushed back that way, and it will do this. But each time it moves there's friction, so it will gradually move slower and slower until it comes to a rest. Stop with or at 90 degrees to the field, that is, it will be vertical. Okay, now most electric motors use electromagnets instead of permanent magnets. State 3 of the features that control the strength of the magnetic field in an electromagnet. So the 3 features that control the strength of the field are the number of turns in the coil. The second is the currents, the size of the currents. Oh, by the way, this is given on page 228 of the revision guide. So we've got the number of turns. We can increase the strength of the electromagnet with the number of turns. We can increase the strength of the magnet by the current, so how much current we're putting through it, and we can change the strength of the magnet using an iron core. Question 5, part A, is one of those awkward questions that's very easy to demonstrate Fleming's left-hand rule hard to put on paper, so I'm going to cheat here. I'm going to use the revision guide to help me to see what it says. So it says, describe how the direction of force can be determined using Fleming's left hand rule. So from the revision guide, using your left hand, first thing is point your first finger in the direction of the magnetic field. That's the first point. The next point is point your second finger in the direction of the current. Okay, and so that means then the thumb points in the direction of the force. 4 marks. I've missed something out. What have I missed out? I've missed out saying that when the thumb, the first finger and the second finger are all at right angles to each other. So they all need to be at right angles to each other. Right, it then shows us this picture, not that clear. What we've got is we've got a balance and there is a wire here that's held by 2 clamps, and that wire is passing in between the poles of a magnet. So we have a balance. On top of the balance we've got this horseshoe magnet, and the wire is passing through the magnetic field. Okay, and it tells us the method. So it says the piece of wire is fixed, that's what the clamps are there for, and it tells us place a pair of magnets in the holder as shown, set the reading on the balance to 0, then switch the current on and get the new reading from the balance. And it asks when there is a current in the wire, the reading on the balance increases. Explain in terms of forces why the reading increases. This is a very clever experiment because if you recall from question 4, we had this example of a wire that when we put the current on, the wire moves. So what we need to be able to do to measure the force, we can't use a normal Newton meter because the wire is just going to move. So we need to hold the wire still and have some other way of being able to measure the force that's on the wire. So what this experiment does is it uses Newton's third law to be able to measure the force on the wire. Okay, so let's see how this works. So when there is a current on in the wire, the reading on the balance increases. Okay, so what can we say? We can say when there is a current in the wire, a magnetic field is generated around the wire, which interacts with the magnetic field of the permanent magnet. So that means hence the magnet and the wires exert forces on each other. Okay. if the force on the wire is upwards, the force on the magnet is downwards from Newton's third law. So there's the force on the wire, which is upwards, which we can't measure directly, but from Newton's third law, for every action, the magnet pushes the wire upwards, there is a reaction, the wire pushes the magnet downwards, so there's a downwards force on the magnet which can be measured on the balance. So it appears as if there was an increase in the mass of the magnet because it's going pushing it downwards. Okay, then we had this calculation question. We're told in one experiment they determined the force was 2.14 millinewtons, given the current, told the length, calculate the magnetic flux density. So we need to be careful with our units. So step one, I'll write out all my information. I'm told that the force is 2.14 millinewtons, so that's 2.14 by 10 to the minus 3 newtons. The current is equal to 0.32 amps. The length of the wire is 0.048 meters, and I want to calculate the value for the magnetic flux density. My equation that I'm going to use is force equals BIL. I could rearrange, but I'm just going to substitute the numbers in. So that gives me that 2.14 by 10 to the minus 3 is equal to B multiplied by 0.32 multiplied by 0.048. So now I can do the calculation, which means that B is equal to, well, let me do it out completely this way just to make it as straightforward as possible. So let's multiply these two parts together. First of all, 0.32 multiplied by 0.048. So that means that 2.14 by 10 to the minus 3 is equal to 0.01536 multiplied by B. So that gives me, now I can say that B is equal to 2.14 by 10 to the minus 3 divided by 0.01536. So put that into my calculator and I get an answer of, that gives me that B is equal to 0.1393 and the units are Tesla. But whenever I write out this answer, I'm not going to write all these decimal points. It tells me give your answer to two significant figures, and the clue here is this is a 3-mark question because it's just a straightforward calculation, but there are 4 marks available. That 4 marks is for noting that we have to give it to two significant figures, so the answer is going to be 0.14. Okay, and now question 6. So many electrical appliances use circular motion using an electric motor, and we had to just identify appliances which could have an electric motor. So things that are used in rotation, so a drill, obviously that has a rotating bit, the electric fan, yeah, the food mixer, yes, that is rotating. The electric iron, no, that's not rotating, so it's not going to be that one. Electric kettle, clearly not. Electric screwdriver, yes, so it is going to be that one. So those 4. It then shows one simple design of an electric motor is shown in the diagram. It has a coil which spins between the end of the magnet. Notice here we have the split ring commutator, and what that does is it ensures that when it's made that half rotation, which we saw in the previous question, it swaps around the contacts, so that means the force is always in the same direction, so it will continue turning clockwise. Okay. So it asks us, give two ways of reversing the direction of the forces in the electric motor. And the first way is to reverse the direction of the currents. So you could say by swapping around the contacts on the battery or switching the battery in the other way around. And the second one is to reverse the direction of the magnetic field. Either of those will reverse the direction of the forces, so it would then turn anti-clockwise. If we did both, then we would continue turning clockwise, because we'd reverse the direction and then reverse it again. Give two ways of increasing the force. Well, we know that we can increase the force from the motor effect. We know that it's going to be given by the magnetic field strength, the current, and the length. So we can have increase the strength of the magnetic field. So that's the B in the equation. Or we can increase the current, which is the I term. And that's